Right. Yeah, okay, it's recording. So we finished last time talking about circular motion. That the example would be like tying a string to a rock and then swinging it around your head, or driving in a circle on a on like a roundabout. But there's another type of circular motion, and in particular, sometimes circular motion is the result of something rotating. That sounds obvious. But I mean, like, it's that there's a type of rotation that we're talking about, or there's two different types of rotation that we're talking about here. So the example to give here is like a merry-go-round. So for a merry-go-round, the edges of the merry-go-round are moving in a circle, right? And so it's not like the car, which is making itself go in a circle. It's like you have a solid thing that's just rotating, and so there's circular motion happening. So we can also talk about circular motion in this context. It's totally fine. However, what we do need to do, if we want to use the formula for centripetal acceleration like we did before, we need to actually figure out a way to convert something like RPMs. We need to convert RPMs, rotations per minute or something, to linear velocity. And the reason I say that is that the formula that we had last time on Wednesday was that the centripetal acceleration, A, or A sub c, the magnitude of it was v squared over r, and that v was the linear velocity, or is the linear speed more precisely, of the thing that was going in a circle. So how do we convert rotations to a linear speed? Because rotations is like 2 rotations per minute. A speed is meters per second, for example. It's not just a matter of, we will precisely talk about angular velocity, basically. But in order to do this, it's easier to first know how to convert the quantity amount of rotations to distance traveled. And the reason we would want to be able to do that is if we can convert amount of rotations to distance traveled, then what we can do is we can say, well, they did 2 full rotations in, say, 1 second. But 2 full rotations is such and such a distance. And so then we could say that they went such and such a distance in 1 second. And that would let us convert from a rotational velocity or an angular velocity to a linear velocity. So we're going to use some geometry in order to understand this a little bit better. So let's just say that this is a top-down view of a merry-go-round. Say it has radius capital R, right? So if we're tracking an object on the edge of our merry-go-round, starting at some initial position there, and it moves to it rotates an angle theta, we can ask how far does it travel? We'll call that S. So from geometry, hopefully you guys remember this, 1 full rotation, well, we know the distance traveled by 1 full rotation, it's 2 pi r, right? That is the circumference of a circle. So, oh, and by the way, this is actually how this is when we're talking about angles, there are 2 different ways of describing angles. There's degrees, which you guys are more familiar with, and then there's radians, which you might be less familiar with. But an important note is that there are 2 pi radians in 1 full rotation. And so you could check this. It turns out to be true that the distance traveled along a circle is equal to the radius of the circle, r, times the angle traveled, theta, in radians. So for 1 full rotation, theta is 2 pi, and hence we would get that for 1 full rotation, the distance traveled is 2 pi r. So with this formula in mind, we can actually get linear speed. So v, speed, is just the time derivative of distance traveled, s, right? So this is a, so I'm talking about scalars now, because velocity is in general a vector, but your direction is changing, and so all we actually care about here is the linear speed, not the velocity. But s, as we just talked about for rotational motion, is just r times theta. So this is d of r times theta dt. And for circular motion, the distance that you are from your origin, the value r, is just a constant. So this is r d theta dt, where theta is the angular displacement that you have. It is how many degrees or how many radians, it has to be in units of radians, by the way, how many radians have you traveled? And so we give this thing a name. We give this d theta dt, we give it the name omega. So this W looking thing is the Greek letter omega. By the way, hopefully you guys have seen theta before in like trig, but the Greek letter that looks like a W, it's like a curly W. It's the Greek letter omega. So, you know, there's W and then there's W, or W and then omega rather. So try to keep that straight. And we use that symbol for angular speed. And later on down the line, we will use the symbol omega with an arrow over it for angular velocity, just as we use a V with an arrow over it for velocity and a V without an arrow for speed. But for now, just consider angular speed. It's basically how many radians do you rotate per second. So with this knowledge in mind that we can convert linear speed to angular speed, or to, that we can write linear speed in terms of angular speed, we can express the form, or the magnitude of the centripetal acceleration another way. The magnitude of the centripetal acceleration is, and I'm going to use capital R for the radius now, just so we can keep everything straight. This is v squared over r. But we know that v for circular motion is just r omega. And so then it would be squared divided by r, so this is just r times omega squared. So this is just another formula for centripetal acceleration. Centripetal acceleration is the thing we talked about for the last 20 minutes of last lecture. It is the center-seeking acceleration. It is the perpendicular component of acceleration when a body is undergoing circular motion. Do we assume the term angular speed because we're only considering particles going in the counterclockwise direction? No, so we're assuming angular speed. So we're talking angular speed here because generally angular velocity has a direction, but when you're just talking about rotation in a single plane, like we are, like imagine that this is like the XY plane. When there's rotation only in a single plane rather than in all three, or rather than in all the different planes it could be rotating in, just like how we can talk about just position as a number rather than a vector, like when we were talking about one-dimensional motion, when we talk about rotational velocity, as long as there's only rotation in one direction, either clockwise or counterclockwise, because we're in a single plane, we can just talk about speed. And if we wanted to be extra precise, we would let, in this case, angular speed could be positive or negative, or rather omega could be positive or negative, and meaning clockwise or counterclockwise. So generally, we take clockwise or counterclockwise to be positive and clockwise to be negative. But again, that's a convention. And actually, that's a convention that relates to the right-hand rule, by the way. Right. Okay, so that's enough for circular motion. This was just to give you a little bit of clarity. So omega is just, it's just defined. Omega is just defined to be d theta dt. That's just all it is. Like it's just, whenever you see d theta dt, just replace it with omega. That's just, that omega is just a shorthand for d theta dt, just like how v is just a shorthand for dx dt, right? Or dr dt. Right, so that's enough with circular motion. We'll use circular motion a lot. It's a relatively useful concept. However, there's another type of multidimensional motion that is also relatively simple that we can talk about, and that's projectile motion. So when people are talking about projectile vomiting, for example, this is the type of motion that they're talking about. Why is acceleration squared and not the derivative? This is a formula for the acceleration. This is not, I can answer that question after lecture. It's because it'll require a bit of time, so just stick around. Right, so another special case of motion is that is projectile motion, which is when only a single velocity component changes. So this means, so the example here is you're only pushing on something in one direction. So like, even if it was moving vertically, if you're pushing only to the right, you're only going to affect its motion going left or right. So the fact that only a single velocity component is changing in this particular example would imply that the acceleration is only, or is in one direction only. So there's a really standard example here that we've actually already talked about a bit, and that's free fall. And the reason why we know this is an example is because the vector g, which is the acceleration vector due to gravity, this is a vector that points downwards. It points only in a single direction. It's not changing direction. It's not some mix of directions. It's just down. So the fact that g, the acceleration vector for gravity, points in a single direction means that free fall, this is an example of projectile motion. Anything undergoing free fall is experiencing projectile motion, and vice versa. Anything that is experiencing projectile motion, well, that's not true. One is a subset of the other. Now, the important part of free fall, when we're talking about, or the important part of free fall in general, is that because g only points downwards, the horizontal component of the motion, say, if you fire a bullet horizontally, the horizontal component is unaffected. If the only acceleration or if the only force is gravity and that causes an acceleration downwards, then the horizontal component of motion won't be affected. And I can prove that to you mathematically. So let's use that feature to derive some equations for projectile motion. So just as before, all we're going to do is we're going to start with a constant acceleration, which of course, so we're going to assume that, let me rewrite this. This is not for projectile motion. I mean, it is for projectile motion because when someone says projectile motion, what they really mean is free fall. But let's just, yeah. So when I say projectile motion often, I'm going to be referring to some sort of free fall on a body with some constant gravitational field. So I'll actually keep that. The distinction between free fall and projectile motion, at least perhaps as the conception that you guys have, is that free fall means you just drop something and let it go, whereas projectile motion means something could have some initial velocity and some initial position, and then it goes and it is a projectile. Technically, they're the same thing, but I'm going to use the phrase projectile motion to describe the situation where there is some initial velocity. So with that caveat aside, let's just continue as we did before. We know what we start with, come on. We know what the acceleration is. It's constant because it's just g. The acceleration is negative g in the j hat direction. And it didn't have to be this, but I'm choosing j hat to be the direction that is up. Like that's just a coordinate choice that I'm making. I could have chosen it to be I hat, and then negative I hat would have been up. The point is just pick some label that you're going to give to the up direction, and then the acceleration vector should be g, should have magnitude g in the opposite direction, right? Because it points downwards with magnitude g. So this is our acceleration vector. It's constant, importantly. It doesn't change with time. So we need to figure out what the velocity vector is. Well, the velocity vector can be written in terms of components, which is vx of t in the I hat direction, plus vy of t in the j hat direction. I'm suppressing the third dimension, by the way, because for projectile motion, it always occurs in a plane. You could always rotate your perspective so that g points downwards and x points in the direction that the thing is being fired. It's never going to turn mid-flight, is what I'm getting at. So we're just going to use x and y. You could include z here, but you don't have to, because again, you could always just choose a coordinate system, such that x points in the forward direction of your projectile. Right, so we can write our velocity vector this way, and our goal is to try to figure out what that velocity vector is. Now, we're going to do much of what we did before, where we just start with our acceleration vector. Come on, scroll down. I hate when it does this. There we go. We're going to start with our acceleration. In this case, it's a vector, and then we're going to integrate it to get the velocity. So because dv as a vector, dt, is equal to the acceleration vector, we have the following statements. So that means dv x dt is the x component of the acceleration, and we know the x component of the acceleration is 0. Similarly, the y component of the velocity, the time derivative of that, is equal to the y component of the acceleration, and that's equal to negative g, because the y component is the stuff that multiplies j hat. And then we integrate. Do the same thing that we did before. You integrate from 0 to t against dt prime. But you're going to have to do it for both of these equations. So we find out that vx of t is v0 in the x direction, or v0 in the x direction. This is the x component of the initial velocity. And vy of t is negative gt. Again, we're integrating, and then you're adding our integration constant, v0 in the y direction. So this is our starting place. And if we wanted to know the velocity vector, we would just plug in these components into our velocity vector formula. We can also obtain the position vector as well. Again, all we're doing is we integrate the velocity vector, and then to get each component of the position vector, we just integrate each component of the velocity vector, and then we add our appropriate integration constant because we're integrating from 0 to t and so on. So we get that our x of t is v0 x times t plus x0. And our y of t is minus 1/2 gt squared. You're integrating a linear function, you get a factor of 1/2 and it becomes quadratic. Plus v0y times t plus y0. And in this case, the vector r is now our x of t in the I hat direction plus our y of t in the j hat direction. So these are our projectile motion equations. Put a star by them. And you could have just as easily done this for any constant acceleration problem. Pick your axis so that the constant acceleration is pointing in, or pick your axes so that your constant acceleration is pointing in one of the directions. And then just write out what your acceleration, or write out what your formula is with those axes. And I'll talk about this in more detail later, but if g wasn't actually g, if it was say 5 meters per second squared, not 10, it would this would still hold. This would still be applied. So everything's open note for this course. So, but you should know these, yes. So there is this is technically all you need. However, things can get a little bit complicated, especially if you're new to this game. So, for example, let me specify. X naught is the x. It is the x component of r at time 0, and y naught is the y component. I'm just giving it a different name rather than r naught sub or comma x of the vector r at 0. Yeah, so these are just initial. These are just the initial positions, just like how v naught y is the y component of the initial velocity. R is the position vector. It represents where the object is. Usually you'll well, yeah, that's enough. So this is fine and dandy, and if you know the initial position and the initial velocity, all of their components, then you're good. But you might ask, what if only the initial speed and the angle are given? So the common types of places where these questions are asked are things like, you shoot a cannonball at 30 degrees angle, 30 degrees above the horizontal at 500 meters per second. How far away does it land? Things like that, right? And so that information that's given could in principle be used to you could in principle solve that question with these formula, but it's a little bit tricky because you're not given v naught of y, you're not given y naught, you're not given x naught, you're not given v naught x. Those are some of that info is contained in the initial setup, this 30 degrees to the horizontal with some initial speed. Yeah, so the trick is we use trig. So the example is 5 meters per second, 30 degrees above the horizontal. And we're just going to draw a picture and use trig. So that means, so we have our horizontal. That means that our velocity vector looks like this. Makes an angle 30 degrees with the horizontal, and it has magnitude 5 meters per second. So what we can do in order to find the components is we can use trig. The components are just the lengths of the legs. That's kind of what a component of a vector is. If a vector represents the hypotenuse of a right triangle, the components are just the lengths of the legs. So in this case, this length here would be v naught in the y. Oh, this is v naught, by the way. It's the initial velocity, right? And this horizontal leg is v naught in the x direction. And so we could do some trigonometry. Sine of 30 degrees would be opposite over hypotenuse. So it'd be v naught y divided by 5 meters per second, because the hypotenuse has length 5 meters per second. Similarly, cosine of 30 degrees would be v naught x adjacent over hypotenuse divided by 5 meters per second. And then you could go and you could actually solve explicitly. So cosine of 30 degrees is square root 3 over 2. Sine of 30 degrees is a half. And so v naught y would be 2.5 meters per second. V naught x would be square root 3 over 2 times 5. Whatever that number works out to be. And then from there, then you know what v naught y is, you know what v naught x is, and then another part that I've left out, which kind of intentionally, is that you weren't given x naught and y naught. But if your question is, how far did it travel? You can just choose where you want x naught and y naught to be. The thing about those values, x naught and y naught, those are kind of just like where are you deciding to put your origin? Where do you want, like at what coordinates do you want your cannonball to start? we could just easily choose, let's just say that our cannonball starts at position 0, 0. If it starts at position 0, 0, then it will land when its y coordinate is 0 and its x coordinate is whatever it is. And then its x coordinate will be the distance that it traveled from its initial position. Right, so, but sometimes those initial values will be given to you and you'll have to use those. It all depends. So let me just go over some general tips of how to solve projectile motion problems. And if you guys want to stick around after lecture, I can actually do one of these examples. I will derive the thing that I'm about to, or I will find the formula that I'm going to give you as an example after this. So first step, draw a picture. Draw a picture and label it. Label it as much as possible. So and then after you draw this picture and you're done labeling it, really stop and think about what actually the question is asking you to do. What information does the question contain? It's super important. And obviously, as you get better at this, you can leave out more and more of these steps. But to begin with, it's important to draw a picture and label it with all the information you have, and then also label the variables that you don't know. So the second step is pick an XY origin. And pick a plus x and a plus y direction. So implicit, when I did this before, when we were talking about projectile motion, a pretty standard choice is you just choose the plus y direction, the j hat direction, to be up in whatever sense up means. But that doesn't have to be the case. You can just you could have picked it to be, you could have picked up to be 45 degrees, or to be could have picked up to be some combination of the x and y axis, like 45 degrees up and to the right. And then you just have to use that coordinate system. Often we choose up to be like the up in the traditional sense of opposite direction of gravity to be positive in the y direction, but it's not required. And sometimes it'll be more useful to choose a different set of coordinates. Regardless of which set of coordinates you choose, though, be consistent. If you choose a set of coordinates, stick with that set of coordinates for the entire problem. Otherwise, you're bound to make a mistake. Scroll. I really need a new tablet. Oh, there we go. Right. Step 3. Find the components of the initial velocity. Now, sometimes this means that your components of the initial velocity will be variables. But like an example would be, a cannonball is fired at an angle 60 degrees above the horizontal and lands 500 meters away. What was the speed? Well, you'd have to use trig, but you don't know the actual length of the hypotenuse. But that's going to be a variable, but you're still going to want to write v naught x. You're still going to want to write sine of 30 degrees, or sine of 60 degrees, is v naught y divided by, say, v, where v is, or divided by v naught. And then you'd want to solve for v naught y in terms of your variable speed. And then you'll use that later on down the road to solve for that variable. But regardless, you're going to want a formula for your speed, or a formula for your two components in the x and y direction for velocity, always, even if it's in terms of variables or in terms of our unknown angles and such and so on. Step 4, write down the equations of motion. These are the equations that I outlined above. Sometimes those equations of motion will be different depending on if you choose a different coordinate system. And note which quantities you know and which you don't. Some people like to circle the ones that they do know and box the ones that they don't. Doesn't matter to me. The point is it's useful to isolate and to really understand or grok which variables are known and which are not. Step 5, solve the algebra. Perhaps after plugging in known quantities. And then rewrite your answer as a vector if necessary. This might be necessary, for example, if the question says, what is the initial velocity vector of such and such a thing? Then you would need to write your answer would need to be number I hat plus number j hat, right? But that's kind of an afterthought, because once you have the components, it's easy to write it in terms of a vector. Last step, most important. Check to make sure your answer makes sense. Super important, because often people will make a mistake somewhere and then they'll end up with something with the wrong units, for example. In that case, their answer doesn't make any sense. Similarly, maybe the question was, you shoot a bullet from the Eiffel Tower northwest. How long does it take to reach the ground? If you get a negative answer, you probably made a mistake somewhere, right? Because the sensible answer is it would take a positive finite amount of time to hit the ground. So a way that could happen is maybe you took the negative of the square root term instead of the positive of the square root term, or something like that. And so you just need to double check and make sure everything makes sense. Now, the example that I can work out later at the end of lecture is the Rangefinding equation. So the Rangefinding equation, it's not actually a specific example. What it is it's a generic example that lets you figure out the distance an object travels given its initial speed v0 and its angle when it's fired at an initial speed v0 at an angle theta relative to the ground. How far does it travel before it hits the ground? And the formula works out to be v0 squared over g times sine theta cosine theta. And I will derive this at the end of lecture if people want to see. It turns out, by the way, that this agrees with your intuition. The best angle to get the most distance is when theta is 45 degrees. So it's a good check. All right.
Wait,
so that's it for projectile motion. You're going to do a lot of examples like these. There's some on the homework, and there will also be there's plenty of practice problems that are available all over the internet for projectile motion practice problems. So make sure to get some practice in on this. We're going to take a step away from projectile motion for a moment and from motion in multiple dimensions to talk about relative motion. So relative motion is the thing that we need to understand if we want to be able to answer questions like, from my perspective, if I'm driving on the highway, how fast does it appear that somebody else is moving? Basically, relative motion is how we characterize motion from the perspective of somebody else who's moving. Motion from the perspective of a moving observer. Because, right, if you're standing still and something's traveling towards you at 100 miles an hour, it would look different than if you were traveling towards it at 50 miles an hour and it was traveling towards you at 100 miles an hour, right? Like you would observe different things. So there's a common example. It's in the textbook. I'll just briefly outline it. Actually, I'll just briefly outline it. I'm not going to write it all out. So, and you'll see these names show up a lot in physics problems. So let's say that Anna is on a train moving north at, say, 100 kilometers per hour. and Charlie is also on the train. Bob is at the train station, is stationary at the train station. Yes, Anna is traveling at the speed of light. So now Anna gets up and runs towards the back of the train. At 10 kilometers an hour. So now you have a whole bunch of different people moving in different ways in different situations, and we want to understand what everybody sees. So we might ask, how fast is she traveling relative to the other observers? Well, from Anna's perspective, I'm going to abbreviate with A, she's not moving at all. Everything else is moving around her, right? That's how perspective works. From Charlie's perspective, Anna is traveling south at 10 miles per hour, or 10 kilometers per hour. The assumption here, by the way, is that the front of the train is the direction that it's traveling north. So if she runs to the back of the train, then that would be south. From Bob's perspective, well, hopefully your intuition will let you understand where this comes from. Anna is traveling north at 90 kilometers per hour. Now, the question is how do these, so these have magnitudes, they have directions. From Anna's perspective, it's just 0 magnitude, so it doesn't need a direction. I mean, assume that like the train is passing in front of him while she's running or something. So the question is how do these vectors, these vector velocities, relate to each other? And the important point is that these are all the observers are viewing the same event, but from different perspectives. They're all looking at Anna because she's fine. Or maybe she's not, maybe she's a train wreck, no pun intended, and something's going on. But everybody's looking at Anna. They're all looking at Anna run. So it's all the same thing, but they're getting different answers. And so the reason they're getting different answers is because they are in different quote unquote reference frames. So that's the language that we use to talk about the perspective of a particular observer. So what we found out from this particular thought experiment is that velocity does not just depend on the moving object. It also depends on the observer. So if the observer is moving, that can affect the velocity that's observed. So what we do is we write, this is how we write these things, we write the velocity of B relative to A. And the symbol that we'll use for that is a velocity vector B rel A, with this all in the subscript. So we have the velocity of A relative to B. This is 90 kilometers per hour in the north direction, n hat. The velocity of the A relative to herself, well, that's just 0, right? The velocity of A relative to C, so from Charlie's perspective, is 10 kilometers per hour south. The velocity of Charlie relative to Bob, on the other hand, remember Charlie's just sitting on the train, Bob's sitting at the train station, this would be 100 kilometers per hour north. And another, we can just include this, the velocity of Bob relative to Charlie. So from Charlie's perspective, Bob is going backwards at 100 kilometers per hour in the, not per second, in the south direction. So the question is how do these relate? Well, it turns out, and perhaps you can just guess, that the velocity of A relative to B is just equal to the velocity of A relative to C plus the velocity of C relative to B. And we can check this. Charlie is the train's perspective, yeah. We can check this. So this should be 90 kilometers per hour north on the right-hand side. This should be equal to A relative to C is minus 10 kilometers per hour north, because that's the same as 10 kilometers per hour south, plus 100 kilometers per hour north. And that is just 90 kilometers per hour north. So it checks out. So in general, the velocity of A relative to B, and I know I'm just repeating what I just said, is the velocity of A relative to C plus the velocity of C relative to B. Also, another feature that we can check here using these two data points is that the velocity of A relative to B is equal to the negative of the velocity of B relative to A, i.e., if A sees B going to the north at 10 kilometers per hour, then B will see A going to the south at 10 kilometers per hour. So both of these are true. They're just true statements about how relative velocity works, at least at low speeds. When we get into relativistic speeds, things change. If you want more details, you can see section 1.8 in the online textbook. All right, so that's all I'm going to say about relative velocity. Well, there's a question or two on the homework that will use this, so keep that in mind. Now I'm going to move on to Newton's laws. So we have a lot to cover here. I might run a minute or two over here just to make sure I can finish my thoughts. But let's jump right into Newton's laws. You know, smart boy Isaac Newton, really big name, invented calculus because the physics at the time just wasn't good enough. You know, pretty smart dude. So 3 famous laws, I suppose 4 famous laws. We're only going to talk about the first 3 for now. Is Newton's first law. First law of motion. And I'm going to write it out in long form in words, just so you can see it at least once written out in words. So objects at rest, or in motion at a constant speed in a straight line. So it's either objects at rest or objects in motion at a constant speed in a straight line will remain, yeah, I think his birthday's Christmas, yeah, will remain in that state, either at rest or in constant motion in a straight line at a constant speed, in that state, unless acted upon by an external influence. You know, Stephen Hawking actually was born exactly 300 years after Newton died. It may have been exactly 300 years after Newton was born. Anyway, I always thought it was kind of funny, but you know, you have enough famous people, eventually people will start to have the same birthdays. Right, so there's a lot to break down in this sentence. But before I do that, I actually want to define some things. So let's talk about a force. So a force has a very specific, has a very specific definition in physics. But colloquially, these are things that are pushes, pulls, or external influences. like in the first law described above. These are all called forces. So unfortunately, it's quite likely that the mental model that a lot of you guys will have for what a force is just isn't right. And so we're going to try to replace it so that you do have the correct mental model for what a force is. So let's first talk about what isn't a force. So force is not, it is very much not a quantity stored in an object. Stored in, possessed by, stored in or possessed by an object. So I never want to hear any of you say or write, this thing has this much force. It's a nonsense phrase. And specifically, things don't have force nor can things, quote unquote, transfer force. Neither of those things make sense when we're talking about force. It's also not how many midichlorians you have, also true. So the point is force is not a thing that something has. Rather, we can give a slightly better definition. So force is an interaction. Importantly, it is an interaction, which means it requires more than one thing. It is an interaction between two objects. I'm going to underline two as well because that's important, which comes in the form of a push or pull. So when this happens, so there's two objects involved for any force. Each object affects the other. That's important, right? I can't apply a force to something without it also applying some sort of force to me. And whenever we're talking about forces, and as an interaction, it's always exactly two objects. There's never three things all acting together. It's one thing acts on another, that thing also acts on the first thing. So I'm going to introduce some new language to you, some new phraseology to better understand forces. And this is the force phrase rule. So when we refer to a force, there's a specific phrase that I want you to use to describe it. You should always use the wording, and I'll give you an example. A type of force here, maybe gravitational force or spring force, and then force on the object experiencing the force by the object exerting the force. So as an example, it would be something like, if I am holding up this, or if I were to drop this pen, right? The force on that pen would be gravitational force on this pen by the Earth. That's how you use the force phrase. So whenever you're talking about a force, please use that language. I'm actually going to explicitly ask you on this next homework, and perhaps on an exam in the future, to describe each of the forces using the standard force phrase rule. So make sure that you remember this. So we're just about out of time. I guess we will have to continue on Monday. Yeah, that's fine. This is a good stopping point. Let me